What up, nerd? My name's Ryan. I did my HSC in 2019, and in this video I'm going to go through projectile motion standard question types. So there are 3 quantitative question types that you'll see for projectile motion in HSC physics over and over and over again, and they are the maximum height question type, the time of flight question type, and the horizontal range question type. In the previous video, I went over the basic theory that you have to know for this topic, as well as the prerequisite knowledge, so click the link at the top right if you want to watch that now. Otherwise, let's move on to the first question type. Alright, first up, maximum height questions. From the previous video, we know that when you launch a projectile, it travels in a parabolic path. What a maximum height question is asking you to do is find the maximum height that the projectile reaches. And you can think about this as the turning point of the parabola. What's the maximum height that the projectile reaches? And so in order to do this question, we have to consider the initial position of the projectile over here. So this is the initial position of the projectile. Initial position of the projectile. And the final position. So now sometimes in some questions, you'll see in the following questions, we consider the final position to be at the end of the projectile's, like it's the end of the projectile's path. But that's not always the case. And in maximum height questions, you consider it, you consider the final position to be here. So you consider the final position to be here. So again, what you need to find is this displacement here, which is the maximum height, which in the HSC you'll notate as SY. Sometimes I'll write it as SY max just to emphasize the point that the value XY max is the maximum height that the projectile reaches. So you'll be given, usually you'll be given some information like the magnitude of the initial velocity and the angle of the initial velocity, and then you'll assume that the acceleration is negative 9.8 meters per second squared unless explicitly stated otherwise in the question, and you'll be tasked with finding SY max. So I'll show you how to do that now. Alright, so the question asks, find the maximum height of a projectile launched at 30 degrees to the horizontal with an initial velocity of 20 meters per second. So I always approach these questions with 3 main steps, kind of 4 actually, but we'll call it 3 main steps. First one being labeling a diagram and breaking the initial velocity vector into its components. If you're not sure how to do that or that sounds unfamiliar, click that video above. I did it in the first theory video. And then the next 2 steps are what's called a SUVAT table, and the third step is kinematic equations. All right, so the first step is labeling the diagram. So I've already drawn a basic projectile diagram here. I've got the initial position drawn here, the initial position drawn here, and because it's a maximum height question, the final position is considered at the peak of the projectile, at the turning point of the projectile. So this is the final position here. The next thing I do is draw an arrow to indicate the initial velocity. Draw an arrow to indicate the initial velocity, and then label that arrow as U equals, what are we given in the question? 20 meters per second. U equals 20 meters per second. And you use U in HSC physics to represent initial velocity, or at least the magnitude of initial velocity. And then what else are we given in the question? Launched at 30 degrees to the horizontal. So that means that this angle here is 30 degrees. Next, we need to break the vector into its components. So this component here would be U of Y. So the Y component of the initial velocity U. And this would be this component here, the horizontal component. We would call this U of X. And I might just erase this thing at the bottom here so I can draw U of X easier. This component would be labeled U of X, being the X component of the initial velocity given here. Also, I would draw, just to remind yourself what you're finding, I draw this here. I'll draw the displacement here that we're trying to find, right? And I would label that as SY max. So the next step is to take this triangle here, take this initial velocity triangle, And in a test, I'd either redraw the triangle or I'd just do what I'm about to do on this thing here. But for the sake of clarity, I'll redraw it just so it's a little more obvious what I'm trying to show. Ooh. So now we're going to put our attention on this initial velocity triangle over here, and we're going to find ux and uy using trigonometry. So first up, we'll find ux. So in order to find ux, we have to think about how is it related to the 30 degrees and the 20 meters per second, because those are the only two pieces of information that we have that are relevant. So first thing is that ux is adjacent to the 30 degrees, and this 20 meters per second is the hypotenuse of this triangle. And if you remember your trigonometry, you know that the trigonometric function used when dealing with adjacent and hypotenuse is cos. So cos of a particular angle is equal to adjacent over hypotenuse. In this case, we have cos of 30 degrees, cos of 30 degrees is equal to adjacent, which in this case is u of x, the thing we're trying to find, divided by 20, which is the magnitude of the initial velocity. And so now we want to try and get u of x on its own. We want an expression for u of x on its own. So right now, the u of x up here is being divided by 20. So in order to get u of x on its own, in order to isolate u of x, we need to do the opposite operation to dividing. So we need to multiply this side by 20 to get the 20s to cancel out. But if we do something to one side of the equation, we have to do it to the other side of the equation as well. So we multiply this side by 20 as well. So then we're left with u of x equals 20 times cos of 30 degrees, cos of 30 degrees. And let's make that green just to keep it in line with previous tradition. Okay, so I know that cos of 30 is an exact value. So what do you do if you don't remember what exact value, well, like what the exact value is of cos of 30? Well, I'll show you the trick that I use. So I say and you don't actually have to show this in your working, but I'm just going to show it for the sake of clarity. Let x equal cos of 30 degrees. Then I go to my calculator and I put in cos of 30, and you get this really ugly number, right? So this number goes on forever. What happens if you square this number? So we square the number and we get a really nice number. So this is 3 over 4 if it was in fractional form, right? So we know that x squared, or cos 30 squared, x squared is equal to 3 over 4. So if x squared is equal to 3 over 4, then x is equal to the square root of 3 over 4. It's actually plus or minus, but ignore that. Okay, x is equal to root 3 over root 4. Now this can be written as root 3, as I just said, root 3 over root 4, and root 4 is the same as 2. And so because we let x equal cos 30, we know that cos 30 here is equal to root 3 over 2. Okay, so then we substitute that back into our equation. I'll just get rid of all this. So root 3 over 2. So we know that u of x is equal to 20 times root 3 over 2. And simplifying this, we just get 10 root 3 meters per second. So u of x is equal to 10 root 3 meters per second. And I'll just write that here. 10 root 3 meters per second. And now that we have the x component of the initial velocity ux, we're going to find the y component of the initial velocity uy. And we're going to use the exact same process. How is uy related to the 30 degrees? Well, it is opposite the 30 degrees. And we still have this value 20 meters per second. It's still the hypotenuse of the triangle. And so what's the trigonometric function we use when we have the opposite of an angle and a hypotenuse? Well, that's, if you remember your trigonometry, that is sine. So sine of theta is equal to opposite over hypotenuse. In this case, our angle theta is 30 degrees. 30 degrees. Our opposite, if you remember from the triangle, is uy, the thing we are trying to find. So our opposite is uy. And our hypotenuse is 20 meters per second, right? Our hypotenuse is 20 meters per second. So doing the exact same process, in order to make uy the subject of this equation, we multiply this side by 20 so that the 20s cancel out. If we do something to one side of the equation, we have to do it to the other. So you need to multiply the left-hand side by 20. And then we're left with 20, or u of y equals 20 times sine of 30 degrees. Sine of 30 degrees is also an exact value. I don't remember what it is. So I go to my calculator, I put in 30, sine of 30. Okay, that's nice. It's a half. So sine of 30 degrees is a half. And so 20 times a half, 20 multiplied by a half is 10. So now we know that uy is equal to 10 meters per second. And I'll just write that back up here. uy is equal to 10 meters per second. So just to recap, in that step, we labeled the diagram, we drew the final position, we drew the thing that we're trying to find, sy max. We also broke the initial velocity into its x and y components, and then we used trigonometry to find the value of the x and y component. So next step, step 2, is the SUVAT table. Now, SUVAT is an acronym for displacement, initial velocity, final velocity, acceleration, and time. And the goal of the SUVAT table is to find out as much data as possible. Find out and collate all the data that you've been given in the question. And so I didn't actually draw a table in an exam just because it takes too long. I just kind of jotted them down on like a free piece of the page. But I did do this every single time. And when you do, it's a really good habit to get into, because when you do more complicated questions, like the ones that you'll see in your final exam, you often cannot quite see how to solve a particular question unless the values are staring at you, like right in front of you. So that's why this is a really good habit to get into. And then I'm going to label all of these x. We don't have to label the t because time doesn't change depending on whether you're moving in the x or y component. So the first thing we're going to do here is see which one of these corresponds to what the question is asking us to find. So in this case, the question is asking us to find the maximum height, and so that would correspond to sy, and I'd like to do a little max subscript there. So sy, and what I would do is sy equals question mark, and that tells me when I glance at the SUVAT table that that is the value I have to find. That is the value I have to find. So, and then we just go down the list, see what values do we know. S of x, do we know anything about the displacement in the x direction? No, we do not know anything. So we just leave that blank. U of x, do we know anything about u of x? Indeed we do, we found u of x. That is 10 root 3. And I'll just make that blue. 10 root 3. Do we know anything about v of x? Not really. Do we know anything about a of x? Well, there's no force acting on the projectile in the x component, right? The only force acting on the projectile is gravity, pulling the projectile down. So there are no forces in the x component, therefore there is no acceleration in the x component. But because the acceleration is 0, we can also say that the final velocity is going to be equal to the initial velocity, right? Because if there's no acceleration, then there's no change in velocity. And so we do actually know what the final velocity x is. Do we know t? Do we know t? What would t be in this situation? Well, t would be the time that it took for the projectile to go from its initial position to its final position. Do we know what t is? No, we do not know what t is. Sy max is what we're trying to find. U of y, do we know what the y component of the initial velocity is? Yes, we do. We found it. It is 10 meters per second. And I will make that red. Do we know what the final velocity is? This is an interesting question. This is the entire crux of a maximum height question that you need to remember. So when you're doing a maximum height question, the final velocity in the y component is 0. Why is the final velocity in the y component 0? Well, if you look at the graph, when you throw a projectile, when you launch a projectile, at the very top of its motion, it's moving from, like, its velocity is going from being in the positive upwards direction to being in the downwards negative direction. That's a turning point, right? So there's an infinitesimally small amount of time in which the object is actually stationary. So when it's at its, or at least stationary in the y component, it's still moving in the x component, but it's stationary in the y component. And so if something is stationary in the y component, that means it has a velocity of 0 in the y component. So at the maximum height, a projectile will have a velocity of 0, a final velocity of 0 in the y component. And that's the trick that you have to remember for all maximum height questions. At the maximum height, the velocity is 0 in the y component. Now that might have been a bit confusing when you're first encountering it. Don't worry, you'll get used to it. The more of these questions you'll do, the more it will just become an instinct. Okay, so what's the acceleration in the y component? Well, that is negative 9.8 meters per second squared. And do we know t? No, we don't know t. So remember, the thing we're trying to find is the maximum height, as denoted by sy max. And we have 3 other pieces of information for the y component. So because the thing that we're trying to find is in the y component, I'm just going to ignore all of this stuff because we're not actually going to need it for the question. So now we're on to step 3. What are our kinematic equations? Well, they are v squared equals u squared plus 2as. There's v equals u plus at, and s equals ut plus half at squared. So these are our kinematic equations. Now what we're going to do is go through each of these equations and find out which one we're going to use. So first of all, the equation that we use needs to have an s because that's what we're finding. We're trying to find the displacement s. So let's see. The first equation, does it have an s? Yes, it does. The second equation, does it have an s? No. So we ignore the second equation. The third equation, does it have an s? Yes, it does. So these are our 2 potential equations. Now we go through and see what data do we have that is included in this equation. Well, do we have we have a uy, and this equation has a u, so that's good. And this equation also has a u. We have a vy. The first equation has a v. The second equation doesn't have a v. Now that's not a good sign, but it's not necessarily disqualifying yet. And let's see. We have an ay. This equation has an a, and this equation has an a. Now all of the variables in the first equation have been ticked. There's one variable that hasn't been ticked in the third equation, and that's t. And do we have a t? No, we do not have a t. So we remove the third equation. Therefore, we're going to be using v squared equals u squared plus 2as. And I've just put the subscript y on each of these variables to remind myself that we're working in the y component. And now what we're going to do is input all the relevant information from the Suvat equation into this kinematic equation and then solve for sy. We're going to solve for this sy, which represents our maximum height, the maximum height of the projectile. So first up, vy is 0 from our table. So 0 squared equals uy squared. What is our uy? It is 10. So 0 squared equals 10 squared plus 2 times ay. What's our ay? It's negative 9.8. That's the acceleration due to gravity, multiplied by sy, which is what we're trying to find. So first of all, I'm going to bring this expression here, the 2 times negative 9.8 times sy, to the other side. So I'm going to bring it to the left-hand side. So this is going to be, and when you bring something to the other side, you have to change the sign, right? So a better way of thinking about that is, actually, let me just expand this a little bit first. So here 10 squared is 100, and here we've got, what's that? Now 2 times 9.8 is 19.6. So we've got 0 equals 10 squared, which is 100, minus 19.6 times sy. And then we're going to bring this 19.6 times sy to the left-hand side of the equation. And I like to think about it as like bringing it to the other side of the equation, but maybe perhaps a better way of thinking about it is plussing 19.6 times sy to each side of the equation. 19.6 xy. So now on the left-hand side, we have 19.6 sy equals 100. And the minus 19.6 times sy and the plus 19.6 sy are just going to cancel each other out to be 0. So there's nothing else other than the 100 on this side. And now finally, we're almost there. We've got sy equals something. Well, right now, sy is being multiplied by 19.6. So to get it on its own, we need to divide by 19.6. And if we do something to one side of an equation, we have to do it to the other. So we have to divide this side by 19.6. And we're left with sy is equal to 100 divided by 19.6, which if we put that in our calculator, 100 divided by 19.6 is equal to 5.10. I'm just going to write it to 2 decimal places. So sy, what's that 6 doing there? Ooh, that's a glitch. Ooh, uh-oh. Okay, I'll be back in a second. All right, so our sy max is equal to 5.10 meters to 2 decimal places. So just in conclusion, the maximum height that the projectile reaches, is 5.10 meters. And if you want to be super specific, you can say above the launch height. Because in more complicated questions later on, you'll see that you don't necessarily have to think about the projectile from like being launched from ground level. It can also be being launched from like a cliff up here down to some lower point down here. And so that's why I'm saying the displacement, the maximum displacement, the maximum height is 5.10 meters above the launch height. Launch height, or in this case, you could say ground level, above the ground. And so just to recap, what we did is we read the question, find the maximum height of a projectile launched at 30 degrees to the horizontal with an initial velocity of 20 meters per second. We labeled a diagram with the information that we were given. We drew the initial velocity vector and broke it into its components, its x and y components. Then we used trigonometry to find those x and y components. And then we filled out a SUVAT table where S is displacement, U is initial velocity, V is final velocity, A is acceleration, and T is time. We filled out all the information that we knew in the SUVAT table. And then we reasoned our way, and not really reasoned our way, but we realized that at the top of a projectile, when a projectile is at its maximum height, it has a velocity of 0 in its y component. And that's really what you have to remember for all maximum height questions. You're always going to, and some questions, even when you're not asked to find maximum height, you can use that fact to find other things. But that you'll see some of those questions later on. And then we determined which kinematic equation that we needed to use in order to solve for SY. And then we put in all the relevant data into the equation and rearranged for SY, and then gave a little concluding statement here. So the next question is a time of flight question. What is time of flight asking for? It's asking for the time t, that it takes to move from the final position, not from the final position, from the initial position, here, so from the initial position here, to the final position, which in this case is here. So the time taken to move from the initial position to the final position. That's what a time of flight question is asking you. And it's in the name, right? What's the time that it takes for this projectile to do its entire flight, right? Again, you'll usually be given an initial, and the magnitude of the initial velocity and the angle that the initial velocity is directed towards. And again, unless it is explicitly stated otherwise, you assume that the acceleration is 9.8 meters per second squared downwards due to gravity. All right, so this question says, calculate the time taken for a projectile launched from ground level to fall back to the ground. The projectile has an initial velocity of 100 meters per second at an angle of 45 degrees to the horizontal. So what do we do first? Label our diagram. Notice how the question said, calculate the time taken for a projectile launched from ground level to fall back to ground level, fall back to the ground, right? So that means it starts here. This is its initial position here, and it ends back at the ground level here. So this is its final position. So you might be thinking, why do I have to label the initial position and the final position? And you have to do this because I guarantee you at some point, if you don't do this, you will screw up the question. I learned that the hard way a variety of times. So the initial position is here and the final position is here. What's next? We label the initial velocity with a vector. We label the initial velocity with a vector. Then we write down the magnitude of that velocity, which in this question is 100 meters per second. And it is launched at an angle of 45 degrees to the horizontal. The next step is that we break this vector into its components. So this is the y component, so uy. And this is the x component of the initial velocity, u of x. And I'll remove this thing again just to make it clearer. Okay, now we take this initial velocity triangle. We take this initial velocity triangle and either we redraw it or we just use our original diagram. Again, I'm going to copy it and move it over here just so it's a little more clear. We use trigonometry to find u of x and uy. So how is uy related to the 45 degrees and the 100 meters per second? Well, it's opposite the 45 degrees and the 100 meters per second is the hypotenuse. So opposite and hypotenuse, that's sine. So sine of the angle, I'm gonna go a little bit faster this time. Sine of 45 degrees is equal to opposite, which is u of y, over the hypotenuse, which is 100 meters per second. Now we want uy on its own, so we multiply this side by 100. And if we do something to one side, we have to do it to the other side, so we multiply this side by 100. The hundreds cancel out, and we are left with uy equals 100 sine 45. And I didn't put a multiplication symbol in between here because if you've got a number and then a sine function, you just assume that it's being multiplied. So again, I know that sine 45 has an exact value, and again, I can't remember what it is, so I put in sine 45 into the calculator. You get this disgusting number. So sine 45 is going to be, I guess I don't really have to say let it equal to x. I can just be like, sine 45 is some disgusting number. If you square that disgusting number, so sine 45 squared is equal to 0.5, so is equal to a half, which we can write as 1 over 2. And then if we square root both sides, we can get that sine 45 is equal to root 1 over 2, which is the same as root 1 over root 2, which is the same as 1 over root 2. So now we know that sine of 45 degrees is equal to 1 over root 2. So we'll substitute that into our equation. So 100 times 1 over root 2. And so now we know that uy has a value of 100 over root 2 meters per second. So uy is equal to 100 over root 2 meters per second. Now we're going to do the same thing for u of x. So how is ux related to the 45 degrees? Well, it's adjacent to the 45 degrees. And again, the 100 meters per second is the hypotenuse of this initial velocity triangle. So we're going to use cos because we have something which is adjacent and we have a hypotenuse. So cos of 45 degrees is equal to adjacent over hypotenuse, which is ux over 100. Come on. Want that to be black. Okay. And now again, multiplied both sides by 100 in order to get u of x on its own, because these hundreds cancel out. ux is equal to 100 multiplied by cos of 45 degrees. Again, I know that cos of 45 degrees is an exact value, but again, I don't remember what that exact value is, so I go to my calculator, I clear it, I put in cos 45, I get this disgusting number. If I square that, again, I get a half. And so cos of 45 is the same as sine 45. So we can say that this is 100, this is 100 multiplied by 1 over root 2. Because we would just be following the same process as we did for the sine 45. And this is equal to 100 over root 2 meters per second ux. And again, I'll write that up here. 100 over root 2 meters per second. All right, now onto our SUVAT table. So displacement, initial velocity, final velocity, acceleration, and time. I'm going to copy that over to the other column. If copy and paste is working. Yeah, okay, there we go. Copy it over to the other column. Write the relevant subscripts. So x, 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 y, 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 y. Do we know what Sx is? So what's the displacement from in the x component from the initial velocity, from the initial position to the final position? What's the displacement in the x component? We don't know that, so we're not going to write anything there. Actually, first of all, what are we finding? We're finding the time of flight. So we're finding this t, or we can think about it as finding this t as well. We don't know Sx, we do know Ux, don't we? That's 100 meters per second over root 2. Yep. Or I should say 100 over root 2 meters per second. I'll make that blue. Vx, what's the final velocity? Well, we know that Ax has there's no force acting on the projectile in the x component, therefore the initial velocity is the same as the final velocity. By the way, that might make you feel uncomfortable, right? Because when at the final position, it hits the ground, right? So shouldn't it just kind of stop? Or not just kind of stop, shouldn't it like rebound or something? So you're right to think that. However, when we say final position, it's actually just above the ground. We're considering it just before it hits the ground, right? So that's the way that you should think about it, just the tiniest distance above the ground. Or you can think about it as the instant that it hits the ground. It hasn't had the interaction with the force from the ground yet to slow it down yet. It's right before it hits the ground. Well, at least that's how I stopped the itching in my head. Anyway, so do we know Sy? Do we know the displacement at the final position? We do know the displacement at the final position. So the displacement up here is some Sy max. So that's the max height. The displacement here in the y component, right? In the y component is something between 0 and the maximum. At the initial point, sy is 0. Sy is equal to 0. And at the final point, it comes back to the ground, right? So at the final position, sy is also 0. So we do know the final velocity, and that's the critical trick for time of flight questions, or for most time of flight questions. The displacement in the y component at the final position is equal to 0 meters, or whatever units you're working in, right? It's equal to 0. In fact, there's not a whole lot of need for me to put units in at the moment. So sy, the displacement in the y component, is equal to 0. What about uy? Do we know what uy is? Yes, we do. It's 100 over root 2 meters per second. And I will make that red. Vy, do we know the final velocity? No, we do not know what Vy is. Actually, we do, but I'm not going to tell you what it is yet. Do we know what Ay is? Well, because we were not told otherwise in the question, we assume that it's negative 9.8. Okay, so now onto our kinematic equations. V squared equals u squared plus 2as. V equals u plus at. And s equals ut plus half at squared. So we are trying to find the time of flight, right? That's the whole point of this question. The second equation has a t. The third equation has 2 t's. The first equation does not have a t, so we ignore the first equation, or we remove the first equation. So the second equation, we have a v, we have a u, we have an a, and we have a t. Now we have all those data points for the x component, right? We have a u, we have a v, we have an a, we have a t. But what would happen if we subbed those into this equation? Well, v is, I'm just going to do it real quick. V is 100 over root 2. U is 100 over root 2. Plus a is 0 multiplied by t. Well, when you have 0 multiplied by t, that's just going to be 0. And now you've proved, congratulations, you've proved that 100 over root 2 is equal to 100 over root 2. That's of no use to us. What about the other equation? Can we use the x component data for the other equation? Well, the other equation requires an s, and we do not have sx, right? So we are not going to use the data from the x component. We're just going to focus on the y component. So it's got a t, and that's what we're trying to find for both equations. Do we have a v? Do we have a final velocity? There is a way to find it, but I'm going to tell you a bit later because there are 2 methods to doing this question, and I want to show you the more common method first. So we don't have a vy, at least at this point, so we're going to ignore this equation. Do we have an s? Yes, we do. It's 0 here. Do we have a u? Yes, we do. We're trying to find the t. Do we have an a? Yes, we do. It's negative 9.8. So we're going to use this equation, and we're going to use the y component data. All right, so let me just make this a little bit neater. Bring this up here, and I'm going to put the subscript y on each of the variables other than t, because t does not depend on whether you're considering the x or y component. All right, so let's sub in our values. Sy is 0. Uy is 100 over root 2. And I'll make that red just to follow the convention. And plus half of ay. So the acceleration in the y component we have is negative 9.8. That's because of gravity. Oh, whoops, I forgot to put the t there. That's a easy mistake you can make, right? So yeah, so ut we have here, half at squared, ay, so a acceleration in the y component is negative 9.8, that's due to gravity, and we multiply that by t squared. So this might look familiar to some of you, hopefully to all of you. I'm just going to find out what half of 9.8 is. Half times 9.8 is equal to 4.9. Okay, so I'm going to rewrite this as negative 4.9 t squared, which is just this term here, plus 100 over root 2 t, plus 0 equals 0. Now what does this look like? This looks like a quadratic, right? ax plus b squared, ax squared plus bx plus c equals 0. It looks like a quadratic. And you might be tempted, okay, I'm going to solve this using the quadratic formula, and you could, but that's really gross. Why do you not have to use the quadratic formula? Well, there isn't a constant term here, and so instead of using the quadratic formula, what you can do is just factorize a t out of this. So if you factorize out a t, you'll end up with this. And this is a little weird, or it might seem a little weird when you first encounter it. You've got something times something equals 0. So for that statement to be true, either the first thing has to equal 0, and I'll move that over here. Either the first thing has to equal 0, or the second thing has to equal 0. And just consider for a moment, like if you had, yeah, oh right, just either this has to equal 0 or this has to equal 0. And if you don't remember that, you just think like, let's say a multiplied by b equals 0. You couldn't have a positive number here and a positive number here equals 0. You couldn't have a negative number times a negative number. You couldn't have a positive number times a negative number. You have to have either a positive or a negative number, let's say 2, multiplied by 0. But if you're not told which of these is 0, then it could be either one. It could be a times 0, or it could be 0 times b, right? So either b could be 0 or a could be 0. That's exactly what's going on here. So either the t, which is outside the brackets, either that is 0 or everything inside the brackets is equal to 0. Now, what does this mean physically? Well, remember what we've put into this equation is, the critical piece of data that we've put into this equation is that sy is 0. And it's telling us when sy is 0, when sy is equal to 0. Well, sy is equal to 0 at 2 points, right? It's equal to 0 at the initial position, and it's equal to 0 at the final position. And so what this is telling us, another glitch. Give me a second. All right, I'm back. If anyone knows how to fix that, let me know. I have to like restart the application each time it does that. It might be like a syncing problem or something. Anyway.
Yeah, you've got to help us. We've tried nothing and we're all out of ideas.
So where were we? Okay. Sy is equal to 0 at the initial position and the final position. So what this equation is telling us is that at t equals 0, Sy is equal to 0. So this is at the very start, right? This is at the start. Hence, this is going to tell us what the time is at the final position. So this is going to correspond to the final position. And we're looking for if you remember, we're looking for the time taken for the projectile launched from ground level to fall back to ground level. So we're trying to find information about this final position here, right? It's getting very messy on this page, but we're trying to find information about this final position here. So this part of the equation is going to give us that information. So we can take the 4.9t to the other side, or we can plus 4.9t to both sides of the equation. Actually, what's a clearer way of saying that? No, actually, I'm going to move this 100 over root 2 to the other side of the equation. So we have 4.9t equals negative 100 over root 2. And that's just minusing 100 over root 2 from each side of this equation up here. Now I'm going to divide both sides by negative 1, or you can think about it as multiplying both sides by negative 1 just to get rid of that yucky negative. And now I'm trying to get t on its own, right? So I'm going to divide this side by 4.9, and I'm going to divide this side by 4.9. Now dividing by 4.9, if you remember from math, is the same as multiplying by 1 over 4.9. And I think it's a little easier to think about if you write it like that. And then we're left with 100 over 4.9 multiplied by root 2. And if you evaluate that in a calculator, I'm just going to do it quickly here. You can check it if you don't believe me. If you put that in a calculator, that's 14.43 seconds to 2 decimal places. So as a concluding statement, we say, therefore, the time of flight for this projectile, time of flight, I'm just going to abbreviate this sentence. The time of flight is 14.43, or is roughly 14.43 seconds. All right, so if you remember at the start, or not at the start, about halfway through, not halfway through, at step 3, I told you that there were 2 methods to approach this question. So I just showed you the method where you use this equation. And I said that the second method relied somehow on us having a final velocity in the y component. Yeah, so I'll address that first. Oh, so messy. So damn messy. I'll just remove some of this here. Okay. So we know what the initial velocity in the y component is. It's pointing up, and it's 100 over root 2. And we also know what the initial velocity is in the x component. Now, this parabola is perfectly symmetrical. So the height here is the same as the height here. As such, or similarly, the velocity of the projectile here is equal in magnitude to the velocity of the projectile here. It's just pointing in a different direction. And maybe a better way to say that is that the velocity of the x component here, for now, is the same as the velocity of the x component here. And the way I should probably have said that is that the velocity of the y component here, let's say at point A, right? This is like point A here, is the same in magnitude of the velocity at point B here, and this is point B, except it's just in the opposite direction now. So instead of being positive, it's negative. So at the start, we know that, sorry that this is so messy. At the start, we know that the velocity in the y component is 100 over root 2. So that's at the very start. That's over here, right? Up here, the velocity in the y component, should write. So yeah, I should write u of y is 100 over root 2. I'll just remove it here, remove it from here. And so the velocity at the end of the projectile, is going to be equal in magnitude, but in the opposite direction. Now, all of this hinges on the knowledge that projectiles are symmetrical. And that's more something you do in math. So this is why I showed you this method second, is because it's usually a lot neater, but it requires more explanation to the marker of why you're able to just say that the final velocity is equal in magnitude to the initial velocity. And so whenever I was doing a HSC physics test, I used the first method just because it doesn't require as much explanation. You just have to say like the displacement at the end is 0. That's really all you have to take. But in order to explain this concept, you have to say, well, it forms a perfect projectile, and it is a projectile, and that forms a perfect parabola, and parabolas are symmetrical, and blah, 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 blah. You have to explain all that before using this. So I would avoid using this, but just so that you know, this is method 2. Method 2. I'm going to probably need more space here. Okay, this is method 2. So what do we know now? We know that Vy is negative of uy, so negative 100 over root 2. And now we can use the equation. Now we can use the kinematic equation V equals U plus AT. And I've put the subscript Y there. So subbing into that, we have negative 100 over root 2 as Vy from our suvat table. We have Uy is 100 over root 2. We have Ay is negative 9.8, acceleration due to gravity. And we have T, remember we're trying to find the time of flight. So the information about the end point that we've put into this equation is this V of y, right? So the information that we put into the equation in the first method about the fact that our projectile is now at the end point of its motion was this sy equals to 0. And now the information that we're putting in instead of that, because like in this second method, there's no s in the equation, right? So we can't put in the information that we're at the end of the projectile's motion because the displacement is 0. We have to put in that information in some other way, right? And in this case, we're putting it in by saying that Vy is equal to negative 100 over root 2. Now, if we plus 100 over root 2 to both sides of this equation, and why the hell not? While I'm at it, we'll plus 9.8 to both sides of the equation. 9.8 times t, I should say. We end up with this cancels out with this. So on the left-hand side, we're left with 9.8 t, 9.8 multiplied by t. And on this side, we're left with 200 over root 2. And then these two cancel out to become 0. And then we want to get t on its own. So we divide the left-hand side by 9.8, and we accordingly divide the next side by 9.8, or the other side by 9.8, which is the same as multiplying by 1 over 9.8, which leaves us with t on the left-hand side, and then 200 over 9.8 root 2 on the right-hand side, and that looks almost the same as what we had before, right? So why is it different? Well, it's the same thing, except it's multiplied by 2 at the top and the bottom, right? So if you multiply the top and the bottom by 2 here, which is the same as multiplying by 1, you'll end up with 200 over 9.8 root 2. And that doesn't change the value. If you put it into the calculator, you get... Actually, I'll just say that we can rewrite this as 100 over 4.9 root 2. And that's equivalent to the time that we got using the previous method, which was 14.43. 14.43 seconds to 2 decimal places. And that's a good sign that we got the same thing, right? That means we did it... Let's not make it all messy like that. We got the same value in method 1 and method 2. So either I made the same mistake twice, or we did it correctly. Okay, so quick recap. For time of flight questions, we consider the initial position to be here and the final position to be here. Given an initial velocity and the angle, we notate that on a diagram. Then we break it into its x and y components, and then we use trigonometry to find those x and y components. We put all the data we know into the suvat table. If we're using the first method, we put in the piece of data that sy is equal to 0. And if we're using the second method, which I do not recommend that you use, but I did it just so you know, if you're using the second method, you'll put in this piece of information. And this is true because this particular parabola is perfectly symmetrical, so the velocity in the y component at the initial position is going to be equal in magnitude to the velocity of the y component in the final position, except with the opposite direction, right? Except with a negative. Oh, okay. Final question type, horizontal range. This question is asking you to find the displacement from the initial position to the final position in the x component. So this is the initial position here, and this is the final position here. Again, you'll be given usually you'll be given some piece of information about the magnitude of the initial velocity and the angle that the projectile is launched in relative to the horizontal level, And again, unless explicitly stated otherwise in the question, you assume the acceleration in the y component to be negative 9.8. So here's an example question. What is the range of a projectile launched with an initial velocity of 1 meter per second at an angle of 45 degrees to the horizontal? And usually I've been writing those in green, so I shall continue to do so. All right, so find the range. So we need to find the distance from the initial position, well, not the distance, I should say the displacement. The displacement from the initial position to the final position, where this is the initial position, and this here is the final position. So a range question is asking us to find this displacement here. Again, like all the previous questions, we draw an arrow. We draw an arrow. Oh, geez. That's not what I want. Okay, we draw an arrow. And we notate it with the magnitude of the velocity, which is 1 meter per second. And then we draw the angle that it's shot at, which is 45 degrees. And then we break it into its y and x components. We break it into its y and x components, where this here is uy and this here is ux. And then we use trigonometry to find uy and ux. And once you get used to doing projectile motion questions, you will reach a point, or you should try to aim to reach a point where instead of going through the whole trigonometry thing, you can, well, you'll still be going through it, but you'll be going through it in your head. Instead of writing out each step, you should just be able to see, okay, uy is equal to 1 times sine 45. And then evaluate whatever that sine thing is. So at a certain point, you should only be using 2 steps. And once you do enough questions, you'll get used to it, because basically all you have to do is look at the hypotenuse, write that first, and then look at uy's relation to the angle, which is opposite. And you know that opposite and hypotenuse is sine, so you write sine of the angle. Right? But I'll go through the process slowly, because I remember when I was first starting, that was too much. That was too many steps in one go. So I'll do it slowly for you, as I would have liked to had when I was in school doing physics. Okay. So again, we take this triangle. And we consider let's find u of y first. We consider what is u of y's relation to the 45 degrees. We know that it's opposite to the 45 degrees. And we know that this 1 meter per second is our hypotenuse. So we have which is opposite, and hypotenuse. So we're using sine. From SOHCAHTOA, by the way. So sine of 45 degrees is equal to opposite over hypotenuse. And because this is 1, this is very simple. So this is just, multiply both sides by 1, and you'll cancel out that 1, and then you'll get uy is equal to sine 45. And I think we had sine 45 previously. Yes, we did, and it was sine 45 was equal to 1 over root 2, and so was cos 45. So this is equal to 1 over root 2 meters per second. U of y is equal to 1 over root 2 meters per second. 1 over root 2. Why am I writing it like that? Clearly tired. Okay, 1 over root 2 meters per second. And if you do u of x as well, which I'll do, so it's u of x is adjacent to the 45-degree angle, so we're using cos. So cos of 45 degrees is equal to adjacent over hypotenuse. So we have u of x over 1. So u of x is equal to cos 45. And we know from earlier that cos 45 is also 1 over root 2. So we have u of x equals 1 over root 2, 1 over root 2 meters per second. And I'll write that on the diagram as well. 1 over root 2 meters per second. All right, now to the second step. Suvat, we have displacement, initial velocity, final velocity, acceleration, and time. Displacement, initial velocity, final velocity, acceleration, and time, I should have said. So then we put on our subscripts. Move that t. Fall in line, t. Okay. So what are we trying to find? What is the range? What is the horizontal range? So we are trying to find s of x here. This is what we are trying to find. S of x. Do we know what u of x is? Yes, we do. It's 1 over root 2. 1 over root 2. And I'll make it the same color. V of x. What is v of x? Well, we know that there is no acceleration in the x component because there is no force being applied to the projectile in the x component. So if there's no acceleration in the x component, we know that the velocity isn't changing. So this is also 1 over root 2. Do we know what the time is? No. What is sy? Well, the displacement in the y component it's 0 initially. Sy initially is 0. And sy finally is also 0. So we do actually know what that is. It is equal to 0. So uy is 1 over root 2. We'll pretend like we don't know what vy is. Ay is negative 9.8. And we don't know what t is either. All right. Ooh, just knocked light. Okay. So now our kinematic equations, v squared equals u squared plus 2as, v equals u plus at, and s equals ut plus half at squared. All right, so somehow we need to find s of x, sx. So this question is a little tricky. We need to find a displacement s, which is contained within the first equation and the second equation. But we don't have enough information we don't have enough information to use those equations. Why don't we have enough information? Well, if we focus on the x components here, what happens if we put in the x stuff? What happens if we put it into the first equation here? Well, we have 1 over root 2 squared plus 1 over root 2 squared plus 2as, where a is 0. And again, we've just proved that, this is an equal sign here. But again, we just proved that, we proved something useless, right? We lost the s term in the process. And the same thing happens with the third equation. If we put in our s of x is equal to 1 over root 2 multiplied by t plus half of 0, all this cancels out. And also we don't even have a t. So we could use this third equation, but we need to, we'd need to find t first. So how do we find t? Well, could we use the second equation? No, we can't, because if we put in acceleration here, the t will cancel out, and we will have just have proved that these two are equal to each other, which we already knew. So what I'm going to do is use this third equation with the y components to find the flight time. So I'm going to do what we did in the previous question. So we're going to find the flight time, and then we're going to use that time to find the displacement in the x direction. So we're going to first we're going to use the information that we know about the y component to find the time that takes the projectile to go from the initial position to the final position. And then we're going to use that time information to plug into some kinematic equations with a bunch of information from the x components to find s of x. That sounds complicated. I'll show you how to do it now. So to find flight time, we're going to do the same process as we did in the previous question. We know that sy is 0, so we're going to use this equation because why not? Sy is 0. Uy, remember we're looking at the y components. Uy is 1 over root 2 multiplied by t plus half times negative 9.8 acceleration due to gravity multiplied by t squared. We're going to factorize out the t's. So we're left with what's half of negative 9.8? That's negative 4.9. Right, so negative 4.9. We're left with this expression. So t equals 0, that's the start. So it's useless to us. And then we're left with 4.9t. I'm just going to speed through this a little bit faster because you've seen me do this before. 4.9 multiplied by t is equal to 1 over root 2. And t is equal to 4.9, t is equal to 1 over 4.9 multiplied by root 2. Now I'm not going to evaluate that because I want it as an exact value, because that's not my final answer. In the previous question, we were trying to find the flight time, so I did turn it into a decimal approximation. But in this question, it's not actually asking for the flight time, we're just using that as a stepping stone to get to the final answer. Okay, so now that we have that, we can use the equation s of x equals u of xt plus half a of xt squared. We know that the acceleration in the x component is 0, so all this stuff cancels out, or all this disappears. Now we have s of x, which is what we are trying to find, equals ux, which we have as 1 over root 2, multiplied by t, which we just found as 1 over 4.9 root 2. And then this becomes 1 over 4.9 multiplied by root 2 multiplied by root 2. Root 2 multiplied by root 2 is just 2, so we have 4.9 times 2. And that gives us 1 over 9.8. And if we put that in a calculator, actually, I'll show you this one. 1 divided by 9.8 is equal to this. So that's 0. I'll do 3 decimal places, 0.102. So the horizontal range is 0.102 meters. Therefore, range of projectile is approximately 0.102 meters. So what did we find again? We found this displacement here. So we found the horizontal distance from the start to the finish. Approximately 0.012 meters. Okay, so quick recap. We labeled our diagram with the initial and final points. We drew the initial velocity vector and broke it into its components. We used trigonometry to find the value of those components. We put everything that we knew into the SUVAT table, and then we found the flight time and then used the flight time to sub into this equation to find the horizontal range. In the next video, I go through projectile motion investigations. So that's all about how we can do experiments to verify the theory that we've learned. And here is the Module 5 Advanced Mechanics playlist. If you don't see the end cards pop up, there's also links to the next video and the playlist in the description. Good luck, and I'll see you in the next video.